Class, good morning. So again, we are going now to proceed to the next topic in power cycle. So this is the ideal Rankine engine. Okay, so take note class, this is not Rankine cycle, but we are going to consider only the Rankine engine. Okay, so let us consider class what is the difference between that. Okay, so we have here class again the basic illustration of the Rankine cycle. Okay. So, the ideal Rankine engine, so is either a steam turbine or steam engine. Okay, so it is clear class. So, it's either a steam turbine or steam engine. Okay? So, the difference between the ideal Rankine engine and the ideal Rankine cycle is that an engine or an ideal engine does not include pump work. Okay, take note class for the engine. It does not include pump work since it is concerned only with all the process occurring inside the engine. Okay, so we are only going to concentrate class our studies on steam engine or a steam turbine. Okay, so it is clear class. Okay, so for the engine to be ideal, the expansion process should be isentropic. Okay, isentropic expansion, as what I have mentioned a while ago or in the previous discussion, that the expansion inside the turbine is isentropic rather. If the expansion is polytropic, it is no longer an ideal. Okay? So let us now class continue our discussion. So the illustration class are the same. Okay? So, for the analysis, so we have here the work. Okay? Work is equals to the difference, of course, of the enthalpies at 1 and 2. So, 1, of course, is the entering enthalpy of the steam from the boiler. Okay? And, of course, its sub 2 is the enthalpy of the steam leaving the turbine or at back pressure. So again class, determining the enthalpy at 2, that is equals to, since S sub 1 is equals to S sub 2, you can say S sub 2 is equals to SF2 plus X SFJ at 2. And then, if you get the value, of course, at the quality rather, so substitute that to h sub 2 equals to hf plus x plus multiplied by hf g at 2. Okay? So it is class. Okay? So next is the thermal efficiency. Okay? So the definition of thermal efficiency does not directly applies to an engine because no heat added to it. Okay? So instead, it is charged with the enthalpy of the steam entering the engine and credited with the enthalpy of saturated liquid at the condensing temperature. Okay? So take note class. We have here the energy chargeable EC. Okay? Energy chargeable against the engine. So that is the enthalpy of the steam entering the engine minus the enthalpy of saturated liquid at the condensing temperature or at back pressure. Okay? So that is class. So the thermal efficiency now is equal to W over energy chargeable. W, of course, is the work, or that is the change in enthalpy, of course, at the engine. Okay? At the turbine. Okay? Divided by the H sub 1 minus the condensing or the enthalpy of the liquid at condenser pressure. Okay? At condenser pressure. Okay, class. So that is for thermal efficiency. Okay? So next, we have here the steam rate. Okay? So steam rate is equals to the total steam flow rate divided by the engine power output. So, AC class. Okay? So take note that the unit of the steam rate is in kilogram per kilowatt hour. Okay, again class, the engine power output is in terms of mass multiplied by the change in enthalpy, which is in kilojoules per kilogram. So multiplied by that kilojoules per kilogram by kilogram per hour, and then changing that hour into seconds, and then eliminate the mass or the mass flow rate or the Trudel flow rate. So the remaining parameters now in determining the steam rate is 360 divided by the change in enthalpy at the engine. Okay, so that is in kilogram per kilowatt hour. Another class is heat rate. So what is heat rate? Heat rate is the energy chargeable per unit of work or the rate of energy chargeable per unit power. So again class, we have here energy rate divided by the power. So mass flow rate times energy chargeable, and then mass flow rate multiplied by W. Okay, so substituting class, the unit mass flow rate is in kilogram per hour, energy chargeable is in kilojoules per kilogram. Again, mass flow rate is kilogram per hour, and then kilojoules per kilogram. Okay, changing again hour to seconds, and then eliminate kilograms, eliminate hour. So the remaining now is kilojoules, kilowatt, and another hour. Okay, so again the equation is ME or 3600 over W multiplied by the energy chargeable, or that is the variant or the variance is ME or the steam rate multiplied by the energy chargeable, or simply the steam rate multiplied by the change in enthalpy, of course, at 1 minus the enthalpy of liquid at condenser pressure, or simply that is in kilojoules per kilowatt hour. Okay? So next class is the relation of the thermal efficiency and the heat rate. Okay? So thermal efficiency is of course the work divided by the energy chargeable. So since EC is also equals to the heat rate times W over 360, and then substitute this equation here in EC. So the remaining now is equals to the thermal efficiency is equals to 3600 over the heat rate. Okay? So this is class similar to the thermal efficiency and heat rate relation and diesel engine. Okay? Or in the performance of the diesel power. Okay? So thank you very much class. So take note class, you study this lesson. So this will become very important as you go with our topics in steam power plant. Thank you very much class.